Alright guys, let's continue with our graphing rational functions and look at a few where we actually have to maybe do some simplifying, and then it does introduce a new type of restriction on the domain that can occur. So for example, if we take a look at this f of x here given, I see the numerator, the x squared plus 7x plus 12 is actually factorable into x plus 4 times x plus 3. And then it's still over x plus 3, right? And that was just using the old factors of 12 that add up to 7 factoring method that we first did a long time ago. And then what ends up happening is, if you think about in the numerator, you have x plus 4, and then you're multiplying by x plus 3, but then you're also dividing by x plus 3. So since it's a factored expression in the numerator, and there's a common factor in the denominator, it actually does just cancel out, right? Because really, like I said, it's x plus 4 times x plus 3, but then you're dividing by x plus 3. So the simplified version, when we want to simplify f of x, it really just equals x plus 4. Okay, but is it exactly the same, right? The line x plus 4, or the function x plus 4, I should say, is just linear, right? X plus 4, graphing just x plus 4 is a y-intercept up at 4 with a slope of 1, right? So it would just do something like this. Okay, now is that exactly identical to what our original f of x would be? Are they the exact same thing? Okay, and the answer is not quite. Okay, and here's the reason why. Okay, and this is a kind of a big key. So f of x, right, this guy, the original rational function here, if you think about its domain, right, x cannot equal negative 3. Okay, because again, when x is negative 3, that causes a big issue where we have a 0 in the denominator. But the function g of x, okay, g of x is just the line x plus 4, its domain is all real numbers. Okay, because it's just a linear function, right? X plus 4, there's no problem. X could be negative 3 for that function, and you're going to get a y value out. Okay, so we just need to be careful when we graph the original f of x that we account for its domain restrictions. Okay, and let's take a look and see how we can do that. Okay, here's a graph. I just threw the, that was the original f of x. I threw that into Desmos just to look at it. And when you see the graph of it in red there, it does look just like the line x plus 4, right? It's just, you can see the y-intercept at 4, and the slope is 1. But I also included this table of values here just so you could see what's going on. Remember we said when x equals negative 3, we have this undefined, and that's because of the x plus 3 in the denominator. So what you guys need to do when you graph something like this, especially if you're relying on technology or whatever, you need to know that there's something going on here, and it's not showing up on the graph. Okay, at negative 3, when you draw this, we're going to see today there's actually a hole right there. And it's just so small that it doesn't show up like on a calculator or a Desmos or something. So when you draw it manually or by hand, you need to actually put an open circle there and make it known that you know there's a hole there. Okay, and we're going to talk about why there's a hole there, because before we had only seen vertical asymptotes, right? And this one clearly does not have a vertical asymptote, where some of the other rational functions did, where they would kind of curve and approach that x value. This one doesn't, okay? But it does not just go clearly right through there. Okay, there is a hole at x equals negative 3 because of this domain, or this expression in the denominator. So let's take a look how it works. Why do some get a hole in the graph while some get vertical asymptotes, and we'll kind of try and put that all together. Okay, so what it boils down to, and if we think about like we did in the warm-up, remember that numerator was factorable. So if we factor that into x plus 4 times x plus 3, and it was still over x plus 3, the difference here and why we get a hole in the graph is because there's a factor of x plus 3 in the numerator as well as in the denominator. Okay, so when x equals negative 3, it would actually cause the numerator to equal 0 and the denominator to equal 0. Okay, and the deal is that having our example had the factor of x plus 3 in the numerator as well as the denominator, when x is negative 3, it really turns this thing into 0 over 0, which is why you get a hole in the graph. So let's look at a few examples and kind of walk through the steps. Having 0 over 0 is actually different than having some other value over 0. Okay, and we're going to see some examples, but this first one right here, when it's 0 over 0, it actually has this name. It's like a, I'm sorry, not it's indeterminate form. And it's like we don't know what's going on. It's like real special where something over 0, it doesn't have to be 1 over 0, but something else over 0 is just considered the undefined like we're used to seeing. But this indeterminate form means like you have to dig deeper, and there's some stuff in calculus that comes up where you have to kind of keep working at things. It's not enough to tell you what you need. Okay, so and take a look at this. Okay, so we're jumping ahead a couple sections. We're going to come back. So let me just take a look here. This is basically saying, so in the graph of a rational function, a break in the graph often signals a discontinuity. That's a fancy word. Functions are going to be continuous if they go through all x values, but these rational functions, we've seen vertical asymptotes are some x values the graph does not go through, so it would not be continuous. Okay, and basically there's two main types that we're going to see in this section. We've already seen the one, vertical asymptotes. Okay, but down here, common factors that are divided out of a function during simplification produce holes in the graph rather than the asymptotes that we have seen so far. Okay, they're called removable points of discontinuity. It's just the fancy term for like when you have a graph going and then there's just a little hole in it and it picks right back up. Okay, so the domain of a rational function does not include values of x where there are holes or vertical asymptotes. So some problems will have both at the same time. Okay, let's take a look. Here's an example A. Okay, they're giving us a nice similar expression to what we saw in the warm-up. Okay, x squared minus 4 over x squared plus 5x plus 6. What we're going to do, you're going to want to factor numerator and denominator if possible. Okay, so the numerator, the x squared minus 4 is the difference of perfect squares, so x plus 2 times x minus 2. While the denominator, the x squared plus 5x plus 6, is similar to what we saw in the warm-up where we can get factors of 6 that add up to 5. So that's why it factored into x plus 2 and x plus 3. And what ends up happening, as we can tell, the x plus 2 factor, when you divide by x plus 2, cancels out. So this is right here is going to be considered our simplified version. We've reduced what we can reduce, but notice this x equals negative 2 is a restriction because it would cause the original denominator to be 0. Okay, and what ends up happening is that x equals negative 2, that's when you get the hole in the graph. Okay, when the factor cancels out, but it was there originally, right? It was in the original denominator. Negative 2 was still a value that would make it 0. That's when you get the hole in the graph. But the x plus 3, once we simplified, the x plus 3 was still there. That's when you get a vertical asymptote. Okay, so you can always just kind of remember the holes come from factors that get canceled out. Vertical asymptotes are ones that are still there. Okay, both of those are discontinuous values or excluded values. So let's do a couple on our own from the beginning. We want to identify any vertical asymptotes and any holes. So in part A, let's just start factoring first. We have the numerator as x squared minus x. So remember, we do have a common factor of x in there, which I can factor out. It would be x times x minus 1. While the denominator, the x squared plus 3x minus 4, we need factors of negative 4 that add up to 3. So we could do x plus 4 times x minus 1. Okay, so we know we're going to have two values of x, right? Looking at the denominator, these all come from the denominator being 0. So I know something's going on at x equals negative 4, and something's going on when x equals 1, right? Those are the values that would cause the denominator's factors to be 0. So to figure out what type it is, you simplify, okay? And if anything cancels out, okay, like in this case, the x minus 1 cancels out, what that means is that the positive 1 is going to be a hole in the graph. Okay, that factor canceled out. It would cause the numerator and the denominator to be 0. While the negative 4 came from that factor, which did not get canceled out, that is going to be the vertical asymptote. All right, let's take a look at another example there. Example B, we have f of x equals 3 minus x over 9 minus x squared. Okay, so same type of deal. It is just a little bit fancier on the factoring, I guess, because things are not written exactly as we would normally probably write them. But the numerator can't really do much with 3 minus x, but the denominator being the difference of perfect squares, it's 9 minus x squared, so it's really going to be 3 plus x and 3 minus x. Okay, we're probably used to seeing x squared minus 9, but this is the same thing. They're still perfect squares. So what that tells me is that we have a factor of 3 minus x getting canceled out, because if we're dividing by it in the denominator. So just be careful. There's still like a factor of 1 up there. It doesn't just completely disappear, because the 3 plus x needs to remain in the denominator. So make sure you don't just put 3 plus x. It needs to be 1 over 3 plus x. And so what that tells us is we have two things. We have two factors in the denominator still, originally I should say. So when x equals, if we set the 3 plus x equal to 0, when x equals negative 3, we have a vertical asymptote because that factor did not get canceled out. Right, that factor is still there. But this factor did get canceled out. When we set that equal to 0, we get x equals 3. Since that did get canceled out, that's when you get a hole in the graph. All right, so putting some of this stuff together, and this goes back, these are these rules now for the horizontal asymptotes, which we saw in the previous section, but just kind of getting them formalized here in the book. So horizontal asymptote, again, before we were talking about vertical asymptotes. So this is now, again, horizontal asymptotes, where you look at the degree of the numerator and the denominator. And remember, there's three options. Okay, if the degrees are the same, that's when you use that ratio of leading coefficients. Okay, we'll look at that in a second. If the denominator is larger, and I always remember this one, like if you have a fraction and the denominator is just bigger and bigger, the whole fraction is really just kind of going towards 0. Okay, the denominator is getting bigger, so you're dividing by a bigger thing, it's going to 0. And the other, third and final case, if the numerator is bigger, there's none. Okay, so there's a couple examples worked out here. If we take a look at example A, okay, right over here, we see the denominator has a higher degree. The denominator is a second degree function, while the numerator is just a first degree function. So when the denominator is bigger, the horizontal asymptote is 0. Okay. In the second example, both numerator and denominator are first degree functions. When they are equal, that's when you use the ratio of the coefficients. So it was 2x in the numerator, 1x in the denominator. So that ratio of 2 over 1 leads you to a horizontal asymptote at y equals 2. Okay, let's just do these last couple real quick, just as a review on that. So example A, we have, if I'm looking at these, we have a first degree in the numerator, first degree in the denominator, so I'm thinking ratio of the coefficients. So the numerator is a negative 1x, so this ratio would be negative 1. The denominator is positive 1. Negative 1 over 1 is a horizontal asymptote at negative 1. Okay. Example B, looking at the degrees, numerator is bigger. Okay, numerator is x squared, denominator is just x to the first. When the numerator is bigger, there is none. There's no horizontal asymptote. Those are the ones they kind of go to infinity. I think we saw one in the previous section. And the last case, numerator is x to the first, denominator is x squared. Okay, when the denominator is bigger, automatically always goes to 0. Okay, so that's the rule on those. Again, that's just a little recap of what we saw before. All right, and finally, let's walk through one full example where we kind of have everything done. I'll just walk you through. This is on the next page here if you're making a graph and trying to get everything set up. So if you take a look, the original f of x is given up here. If you notice things are factorable, generally you want to start factoring, so that's kind of what's going on here. The numerator can be factored into x plus 5 times x minus 2, while the denominator is x plus 2, x minus 2. So once you start simplifying, if possible, and some of them you can't, but the x minus 2's right here you see cancel out. So here's our simplified version down here. Okay, now what that means for us is that since the x minus 2 canceled out, that means there is a hole at x equals positive 2. And since there is still an x plus 2 factor, even after simplifying, it's still there. That's why you get the vertical asymptote at x equals negative 2, which you see right here on the graph. There's the vertical asymptote. Okay, they did a few steps here to get the intercepts like we did before. And when you graph these, you can graph the simplified version if you want to. It's a little easier. You just need to know that there's a hole, or there may be a hole. This one does have a hole at x equals 2. So make sure when you're graphing the function, you clearly indicate. You can see they kind of did it here a little bit, but make it a nice big clear indication that there's a hole there, because again, that was a factor that got canceled out. Okay, so that kind of walks you through the setup. Feel free to use, Desmos or whatever to help with the graph to see where the branches are, but make sure we're clear on setting the rest of the properties up and stuff like that without relying too much on just technology. Okay, so that's simplifying expressions and graphing rational expressions with holes and vertical asymptotes.